Good afternoon. This is Introduction to Robotics, Chapter 1. So the term robot means different things to different people. For some people, even a remote control car that has wheels can be considered as a robot. But as we go along this chapter, we will see that a robot always performs certain tasks. I mean, you wouldn't build a robot that doesn't do anything, and a robot would should be able to sense its environment and sense itself. For example, a robot should know if there are obstacles in its path, and sometimes, or most of the time, a robot would sense, you know, the amount of current that is drawn by its motors, the amount of torque that is exerted, and so on. And a robot also plans. For example, if we use a robotic arm to pick an object, the robot should have its path from initial position and orientation to the pick position and orientation. So the path should be planned, and finally it should act on the task itself. So these are some of the features of a robot that we would encounter in this course. But one thing is certain though, robotics will be an important technology in this century. And as you know, products such as vacuum cleaning robots have already been with us for over a decade, and self-driving cars are coming. So these are the vanguards of a wave of smart machines that will appear in our homes and workplaces in the near to medium future. In the 18th century, the people of Europe were fascinated by automata such as the Cansons Duck shown in the figure. So this is a Cansons Duck. It was invented in 1739, and it was an automaton that could flap its wings, eat grain, and defecate. It was driven by a clockwork mechanism and execute a single program. So apparently there are gears and belts that would enable certain motion and certain tasks to be performed. These machines, complex by the standards of the day, demonstrated what then seemed lifelike behavior. The duck used a cam mechanism to sequence its movement. So let's see a video to give you a picture of how it works. So of course this video is from YouTube and you can always browse it there. So this looks pretty scary because this seems to be an actual carcass of a duck. So apparently that guy had so much love for its pet duck that when he died, he had to bring it to life again. Please don't do this at home. Well, you can do it, just don't bring it to class. Alright, I think you get the picture. So Vaucanson, the same guy, went on to explore mechanization of silk weaving. Jacquard extended these ideas and developed a loom, which is a weaving machine. Shown in the figure, there was essentially a programmable weaving machine. So as you can see here, the Jacquard Loom, invented in 1801, was a reprogrammable machine, and the program was held on punched cuts. So these are punched cuts. These are the early generation of computer programming, where based on these holes, the machine will perform a certain way, will carry out tasks in a certain way. So the patterns to be woven was encoded as a series of holes on punched cuts. This machine has many hallmarks of a modern robot. It performed a physical task and was reprogrammable. So this is our early definition of a robot. It has to perform a certain physical task and it has to be reprogrammable. Let's watch another video.
This is a mechanical Jacquard loom. This technology was developed in France in 1803 by a weaver named Joseph-Marie Jacquard. The key thing about this loom is that it controls every warp thread, the threads that go from the front to the back of the loom, individually. Because it can do that, the loom can create very complex, fancy patterns in the cloth more quickly and with greater accuracy than the technology available before this loom was developed. These cards are what carry the instructions that are read by the apparatus on the second floor that tells the loom what pattern to create. The holes in the cards are read by a series of pins up in the apparatus, and those holes tell the apparatus which threads down here should be raised for each pass of my shuttle across the warp. Some of you might recognize these cards as looking similar to computer punch cards. Back in the early days of computer technology, punch cards carried instructions that told the early computers what kind of calculations to do. So this loom is the great-great-great-grandfather of the computer technology that we all use today, and that technology started with a machine that produces cloth.
So as you saw, the mechanism is pretty complex, and the guy who invented this must be a real genius. So these days we don't need punch card anymore. We can just use computer programming to program our computer or microcontroller that carry out tasks. So that really simplifies our design in a significant way. So the first patent for what we would now consider a robot was filed in 1954 by George C. Devol and issued in 1961. The device comprised a mechanical arm with a gripper that was mounted on a track, and the sequence of motions was encoded as magnetic patterns stored on a rotating drum. So this is the plan view of the machine from Devol's Pattern. And the first robotics company, Unimation, was founded by Devol and Joseph Engelberger in 1956, and their first industrial robot shown in the figure was installed in 1961. So this is the first Unimation robot working at a General Motors factory. And the original vision of Devol and Engelberger for robotic automation has become a reality, and many millions of arm-type robots, such as shown in figures 5 and 6, these ones, have been built and put to work at tasks such as welding, painting, machine loading, unloading, electronic assembly, packaging, and palletizing. So these are some of the tasks that we use robotic arms for these days, and many other tasks. The use of robots has led to increased productivity and improved product quality. Obviously, when you use robots, it can do things or tasks fast and consistently. So this would certainly increase productivity and improve product quality. So let's watch a video on the Unimation robot.
Born in Brooklyn in 1925, Joseph was an American physicist, engineer, and entrepreneur. Growing up in Connecticut during the Great Depression, he returned to New York City for his college education. He pursued degrees in physics and electric engineering from Columbia University. He met George Devol, a colleague and owner of a patent for a basic industrial robotic arm in 1956. When the company they worked for closed their division, finding themselves without a job but with an idea, they founded the world's first robotics company, Unimation. The two men collaborated to design and produce a robotic arm based on Devol's patent. They installed the first unit of the Unimate robotic arm at the General Motors plant in New Jersey in 1961. The arm completely disrupted the car manufacturing industry. Chrysler and Ford soon followed General Motors and started deploying Unimate's arms in their manufacturing facilities. 5 years later, Engelberger and a Unimate robots were guests on The Tonight Show. After leaving Unimation in the 80s and seeing his parents age, Engelberger saw an opportunity for robotics to improve the medical field. He founded Transitions Research Corporation in 1984, selling the first helpmate robot unit in 1988. Within the next 10 years, over 100 hospitals worldwide were operating helpmates. Even after leaving his company and being in his 80s, he remained a very active member in the field and in the community. Joseph Engelberger surpassed himself to develop his companies and democratize robots.
Okay then, you can proceed watching this video on YouTube if you want. So that was Unimation. And this is a modern 6-axis robot designed for high accuracy and throughput. It's ABB robot, and this is Baxter 2-armed robot with built-in vision capability and programmable by demonstration, which most of the robot is able to. Designed for moderate throughput piecework. Baxter has sensors on its joints, and whenever it comes in contact with an object or with a person, it will stop automatically. So Baxter is pretty safe to be used around human beings. Whereas robots such as this kind of robots, which is bulky, normally we have a cage around it so that it will be safe for humans to work around robots such as this. These first generation robots are fixed in place and cannot move about the factory. They are not mobile. So the robotic arms that we saw earlier, such as the ABB, Baxter, Unimation, and so on, they are called robotic arms and they are fixed. By contrast, mobile robots, such as shown in figures 7 to 12, can move through the world using various forms of mobility. And this is a small autonomous underwater vehicle. They can locomote over the ground using wheels or legs, fly through the air using fixed wings or multiple rotors, move through the water or sail over it. This is a UAV. This is a Mars Science Lander Curiosity, where the mast contains 2 stereo camera pairs from which the robots can compute the 3-dimensional structure of its environment. This is a Savioki relay delivery robot. This, as we will see later, this is considered a service robot because it works around human beings, and normally it provides some kind of information to humans who interact with it. And commonly this can be used in hotels, in airports, and maybe in hospitals, so that it can guide patrons or visitors or guests over a certain information that is required. And this is a self-driving car, as you all know. An alternative taxonomy is based on the function that the robot performs. So before this, we have roughly categorized robots into robotic arm and mobile robots, right? And robots can also be categorized into manufacturing robots, service robots, field robots, humanoid robots, and as we will see later, the tele-robotics. So manufacturing robots operate in factories and are technological descendants of the first generation robots. So not only robotic arm, but a mobile robot such as AGV is also considered as manufacturing robot. Service robots, like we saw earlier, the Savioki relay, supply services to people such as cleaning, such as the vacuum cleaning robot, personal care, medical rehabilitation, or fetching and carrying as shown in figure 10. Field robots such as shown in figures 7 and 8. These two, normally they are used outdoors. Work outdoors on tasks such as environmental monitoring, agriculture, mining, construction, and forestry. So, of course, in the field, for certain application, not only these robots are used, 7 and 8, but there can be autonomous trucks, you can have drones, and so on. You can even have drones in manufacturing industry or area. Humanoid robots, such as shown in figures 13 and 14, have the physical form of a human being. They are both mobile robots and service robots. So as you can see, the category can be overlapping, can be a bit confusing, but it does not really matter. But all you have to know is that there are various robots that can be applied depending on the application and needs. So this is the Hubo robot that won the DARPA Robotic Challenge in 2015. A manufacturing robot is typically an arm-type manipulator on a fixed base, such as figure 5, that performs repetitive tasks within a local work cell. So where is figure 5? So this one. And as I've explained, an AGV is considered a manufacturing robot as well. So parts are presented to the robot in an orderly fashion, which maximizes the advantage of the robot's high speed and precision. And well, this is the one of the main reasons why we use robot arms in manufacturing, because we would like to take advantage of its high speed and precision to increase productivity. So high-speed robots are hazardous, and safety is achieved by excluding people from robotic workplaces, typically placing the robot inside a cage. In contrast, as I explained earlier, the Baxter robot is human safe. It operates at low speed and stops moving if it encounters an obstruction. Field and service robots face specific and significant challenges. The first challenge is the robot must operate and move in a complex, cluttered, and changing environment. Because if you consider a robot like the UAV, unmanned aerial vehicle, it has to fly through the air, avoid obstacle, plan its path, and safely take off and land. And a delivery robot in a hospital, like the Savioki relay, must operate despite crowds of people and a time-varying configuration of parked carts and trolleys. So same thing, if you have a delivery or service robot in an airport, not only it has to interact with human beings, it has to keep on moving in a cluttered and changing environment. There can be people's luggages, there are shops all around, people are walking here and there, so it has to move and carry out its task without bumping into anything. A Mars rover, such as shown in figure 9, must navigate rocks and small craters despite not having an accurate local map in advance of its travel. So this is even complicated because a Mars rover can be thousands and thousands of kilometers away from Earth, and how would you control it? So as we will see later, we will talk a bit on aspects of control. How can you control a robot which is very far away? Robotic or self-driving cars, such as shown in figure 11, must follow roads, avoid obstacles, and obey traffic signals and rules of the road. So you can imagine, if you are told to design a self-driving car, how would you do it? If each and every car on the road is autonomous, then things are simpler. However, for the time being, we still have human drivers. So you can imagine the behavior of drivers and the way people drive can be chaotic, can be very complex. So as a designer for or creator for a self-driving car, you have to consider everything: the road conditions, lighting, worn out traffic signals, worn out lines on the roads, many things to consider. So these are the challenges. So the second challenge for this type of robots is that they must operate safely in the presence of people. The hospital delivery robot operates among people. The robotic car contains people, and a robotic surgical device operates inside people. So because humans are involved in the application of these robots, obviously, so the safety of humans is a big issue that we have to consider when we design and build a robot. So what is a robot? Earlier we saw that a robot has to perform a certain task and it has to be reprogrammable. So a common definition is a robot is a goal-oriented machine that can sense, plan, and act. So goal-oriented machine means it does perform certain tasks that would assist human beings. And of course, it has to be able to sense, plan, and act. So we can achieve this by programming and reprogramming our robots. A robot senses its environment and uses the information together with a goal to plan some action. The action might be to move the tool of an armed robot to grasp an object, or it might be to drive a mobile robot to some place. So if you think about a robot arm used in a factory or in a production line, and if the task is to pick an object from a conveyor, so the robot has to have some information on where the object is, or whether the object has come to its predetermined location. So we need sensors for that. So a simple touch sensor or an infrared sensor would do. So whenever the robot knows that an object is present, it has to plan from its initial position orientation to the position and orientation of the picking pose or picking motion. So it has to plan how it should move from A to B in order to pick an object. So therefore, sensing is critical to robots. You need sensors to give an information to the robot of how things are. So proprioceptive sensors measure the state of the robot itself, the angle of joints on a robot arm, the number of wheel revolutions on a mobile robot, or the current drawn by an electric motor. So as you have learned in your control engineering courses earlier, in order to control the angle of a robot arm, let's say to 45 degrees, you need feedback all the time. You need to know what is the current angle of the robot arm. If the current angle is 30, so 45 minus 30, the error is 15. So therefore, your controller should instruct your robot arm to move further so that eventually your robot arm will get to 45 degrees. So sensors that measure itself, the state or the condition or the quantity of itself, is called proprioceptive sensors. There are also exteroceptive sensors that measure the state of the world with respect to the robot. For example, a simple bump sensor on a robot vacuum cleaner to detect collision, a GPS receiver, a compass, or an active sensor that emits acoustic, optical, or radio pulses in order to measure the distance to points in the world based on the time taken for a reflection to return to the sensor. So a simple ultrasound or ultrasonic sensor is an active sensor. A camera, which is getting more and more important, is a passive device. It's passive because it just captures the light, right? Captures the patterns of optical energy reflected from the scene. And we know from our own experience is that eyes are a very effective sensor for recognition, navigation, obstacle avoidance, and manipulation. Vision has long been of interest to robotic researchers. So if you master computer vision in relation to robotic, you can do many things. So that's why self-driving cars these days, they are focusing on computer vision or machine vision, because if you can really do it well, you can get rid of other sensors. Robotic vision system is currently a vast developing area. Figures 15 and 16 show some very early work on reconstructing a three-dimensional wireframe model from a single two-dimensional image and gives some ideas of the difficulties involved. So let's look at these figures. So this is an original picture, right? So we want to get a mathematical representation of this image so that we can do some computation, manipulation, and plan and act. And we want to have something like this. So this is not just a drawing, but we have the coordinates for these lines and edges, or points and edges. So from here we would get this, which is a gradient image. So the way we construct is simply by computing the difference between the pixels. So if it's a black pixel, this pixel here minus this pixel here will probably be 0, therefore you have nothing. But whenever this pixel here minus a pixel over here, you'll get a non-zero value, therefore you have this line. So basically that's the process to get the gradient image. From here we should get the coordinate of each point, and from here we have to construct straight lines. So that's how we get this information from this two-dimensional image. So this is a three-dimensional information. So another approach is stereo vision, where information from two cameras is combined to estimate the three-dimensional structure of the scene. This is the technique used by humans and robots. For example, the Mars rover shown in figure 9 has a stereo camera on its mast. Machine vision is the use of computers to process images from one or more cameras and to extract numerical features. So this is the definition of machine vision. For example, determining the coordinate of a round red object in the scene, or how far a robot has moved based on how the world appears to have moved relative to the robot. So if the robot's environment is unchanging, things are easy. So imagine if you have to drive your car from one point to another only by using GPS information, and you are told to drive with your eyes closed, and the environment is not changing, which means there are no other people there, you are the only one on the road. So most probably you can do it safely. However, in reality, our roads are not stagnant. It's always changing. It's dynamic. So to deal with this, you need to look outwards. So therefore, you need sensors to sense the world and plan your actions accordingly. For humans, this is easy because we have eyes, we have ears, and our brain has been evolved over hundreds of thousands of years to process information. But it's not easy to program a machine to do the same. So this is the challenge of robotic vision. So this is another category of robot, so to speak. Telerobots. These are robot-like machines. So it's called robot-like. It's not exactly robot because humans has to operate it in one way or another. So these are machines that are remotely controlled by a human operator. Because they are remotely controlled by human operator, they don't really fall under the category of robots. Because as we saw earlier, a robot has to sense, plan and act by itself. So perhaps the earliest was a radio-controlled boat demonstrated by Nikola Tesla in 1898, and which he called a teleautomaton. According to the definition above that we saw earlier, these are not robots, but they were an important precursor to robots and are still important today for many tasks where people cannot work but which are too complex for a machine to perform by itself. So for example, the underwater robots that surveyed the wreck of the Titanic were technically remotely operated vehicles, ROVs. Same thing if you have a remote controlled car or remote controlled mobile robot. So they don't really fall under the category of robot because you control it. And it falls under the category of telerobotics. A modern surgical tool shown here also teleoperated. The motion of the small tools are remotely controlled by the surgeon, and this makes it possible to use much smaller incisions than old-fashioned approach where the surgeon works inside the body with their hands. So here we have actual surgeons who will be controlling these robots remotely from a distance. So the advantages of this is that if previously a surgeon has to cut open a patient, and that would leave scar and perhaps increase risk of other problems. So with this technology, they just need several holes to to do an operation or to do something inside your body. So let's look at some strategies of control in the next few slides. The various Mars rovers autonomously navigate the surface of Mars, but human operators provide the high-level goals. So from Earth, first of all, if they send information to a robot on Mars, it would take several minutes. So you can imagine you cannot control everything from Earth because of the time delay. So you can only provide some high-level tasks or goals to the robot on Mars. So perhaps you can give the coordinates where the robot should navigate to and from. And the local decision is done on Mars by the robot itself, which means the robot would determine the details of the route by itself. So the robot on Mars would sense the environment, would plan its path to go from A to B, and finally you would navigate from A to B. But the information on where is A and where is B has to be given from Earth. So local decision making on Mars is essential, as I said earlier, given that the communication delay is several minutes. Some robots are hybrids, and the control task is shared or traded with a human operator. In traded control function is passed back and forth between the human operator and the computer. For example, an aircraft pilot can pass control to an autopilot and take control back. So this is traded control. So for certain task or in a certain time, the machine is fully controlled by human beings or the operator, and in another scenario or situation, it's passed to the machine itself to do everything by its own. In shared control, the control function is performed by the human operator and the computer working together. For example, an autonomous passenger car might have the computer keeping the car safely in the lane, while the human driver just controls speed. So this is safe in terms of operation, because if your bad luck, if your car doesn't carry out the tasks as desired, you can always brake or release your acceleration pedal. And similarly now, if you have been in expensive cars like BMW, it has its self-parking mechanism. And if you have experienced it, the way it does is that you can press a button where the machine or the car will perform its own parallel parking. But in order to do that, the machine or the car with its display will instruct you when to press the acceleration and when to brake. But the turning of the steering will be done by the car itself. So this is more or less shared control, because a human driver will be controlling the pedals and the car will be controlling the steering wheel in order to parallel park safely. So now let's look at robots, jobs, and ethics. I think this part you can read yourself, because in the future you will be the roboticists or the robotic engineers. So you should be able to discuss and debate on issues such as robots taking jobs from people. Of course, on one hand, people might accuse that robots are taking jobs away from people, right? If those days there are many human operators in factories, but these days with the advent of industrial revolution and industry 4.0, they want to implement more robots in order to make things fast, to increase productivity, to increase the economy of a country, to reduce mistakes or rejected parts, to improve consistency in the quality of products, and so on. So these are the trade-offs. So you as future engineers should be able to discuss and to put on the table the various advantages and disadvantages. And how about when it comes to self-driving cars, right? If anything happens, who are to be blamed? And is it really beneficial to have self-driving cars on the road? Can it really reduce accidents and improve traffic as the proponents of self-driving cars suggest? So you should be able to discuss this. And how about you? Will you be daring enough to be in a self-driving car and give the full control to the car or the machine? And how about in healthcare or elder care or child care? Is it ethical to have your parents to be taken care by a robot? So I want you to read this subsection of this chapter and discuss among yourselves on the various issues that might arise from the application of robots. So that's all for chapter 1. I hope you have gained some insights and have some knowledge on what robots are, what is the definition of robots, what are the various categories that we have looked at, what are the various types of robots that you can apply in different applications, sensors that are involved in robot, why robots need sensors and the categories of sensors, cameras or computer vision or machine vision, what are the benefits of having machine vision capability in robots, and finally, robots, jobs, and ethics. So I'll see you again in the next chapter. Thank you for listening.